Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So my name's Emily Prud'hommeaux. I'm a graduate student at the Center for Spoken Language Understanding at Oregon Health and Science University. And I work with Brian Roark. And today I'll be talking about graph-based alignment of narratives for automated neurological assessment. So to motivate the problem a little bit, I'd like to point out that neuropsychological exams often rely on spoken responses elicited by different types of stimuli. For instance, you might be asked to name as many vegetables as you can in a minute, or you might listen to a narrative and then have to retell it. And of course, these are usually part of normed instruments. So there are standardized scoring procedures that are usually carried out on the responses, but you can also think of the responses as a source of language data that could be analyzed for other kinds of diagnostic markers. So I'll be talking about narratives today. There are different kinds of narratives that can be elicited. Personal narratives, you can do narrative generation where you narrate a picture book or a story from a series of pictures or a cartoon or a video clip. Or this is one of the most common ones, is that the subject listens to a story and has to retell the story to the examiner. And that's usually scored in terms of how many story elements were used. So there's information in the original story, and they're graded on how well they replicated that information. Now, seniors with Alzheimer's dementia produce fewer of these key story elements in their narrative retellings. And so the question here is whether we can use these narrative scores to detect very early stages of dementia. The earliest stage of dementia that's usually recognized is called mild cognitive impairment. And I'll talk a little bit about that in detail shortly. So can we identify it? Can we identify MCI using these narrative scores? And also, can we do it automatically? Because we're computer scientists and we like to do things automatically. So the goal is to develop an objective automated tool for MCI, for detecting MCI, that relies on scores derived from narrative retellings. And the way we're going to do this is to think about retelling as a kind of translation. So imagine that the story, you hear it, and you translate it into your own language. It's the same language, but it's your own special idiolect of that language. So I'm going to use existing word alignment tools that are used for machine translation to create machine translation style word alignments between retellings in a source narrative. And then I'm going to improve those alignments using a graph-based method. And then I'm going to extract scoring information from the alignments and then use those scores as features for diagnostic classification. So a little overview of the data. I mentioned mild cognitive impairment. It's characterized by impairments in cognition that are significant but don't interfere with your daily life. So you can still drive your car and balance your checkbook, and you know who your grandchildren are and all of those things. But it is clinically significant. It's real. It's happening. Your cognition is starting to decline. But because it's so subtle, it's very hard to detect with something like the mini mental state exam, instruments like that are usually used to screen for dementia. So MCI is usually diagnosed with a long interview by an expert between the patient, and also with someone who can corroborate what the patient says, like a spouse or other family member. And we're going to use the clinical dementia rating, which is one of the techniques for diagnosing different levels of dementia. And it is one of these interview-based techniques. Typical aging is a clinical dementia rating of 0. MCI is a clinical dementia rating of 0.5. This is how we'll interpret it. Severe dementia would be like a clinical dementia rating of 3. And I'd like to point out the diagnosis does not rely on any narrative recall test. So the narrative recall task I'll be talking about is completely independent of the process by which MCI is diagnosed. So this is our data. We have at OHSU, we're a medical school, we have something called the Leighton Center for Aging and Alzheimer's Disease Research. And they have this very long NIA-funded longitudinal study on brain aging where people come in and they give them the mini mental state exam. They have them do a bunch of activities and tests and their interviews. And during this exam, they're given the interview by which you can diagnose MCI. And so we have 72 subjects with MCI and 163 subjects without. There are no significant differences in age or years of education. And there's also additional 26 subjects who have more advanced dementia, or were too young to be eligible for this study, or had a diagnosis that changed back from MCI to typical aging. And so we didn't want to include them in either diagnostic group since it's not clear which one they're actually in. The narrative task we'll be talking about is the Wechsler logical memory subtest of the Wechsler memory scale. The Wechsler memory scale is a widely used instrument used to assess memory in adults. It's been used for 70 years. And the story that we'll be talking about has actually been used for 70 years as well. So the examiner reads a story to the subject, and the subject has to retell that story immediately and then after a 20-minute delay. And the score is how many story elements were used in each retelling. And the identities of the story elements are noted, but they're not reported. They're not used as part of the score for the Wechsler memory scale. This is the narrative itself. And you can see that the slashes denote the boundaries between elements. So there are 25 story elements. This is a sample retelling. And the underlined items are the correctly recalled elements. So you can see that Anne is a correctly recalled version of Anna, but Taylor is not a correctly recalled version of Thompson. And that's because these published scoring guidelines give pretty explicit directions about what are acceptable lexical substitutions and what are not, what sorts of paraphrases would be acceptable. And this person gets a score of 12 out of 25. So I mentioned that I'm thinking of retelling as translation and that I want to do word alignment. So instead of translating from German to English, I want to translate from the story to the way someone rendered that story. And so the way statistical machine translation works typically is you begin with this sentence, parallel corpus of sentences, where you have sentences in one language on one side of the corpus and translations of those sentences on the other side of the corpus in a different language. And the idea is that you need to figure out which words are translations of which other words. And the way you do that is through word alignment. And this could be easy. It could just be like you just monotonically go through and line them all up, or it could be really complicated where there's lots of word order differences and things like that. So you can't just use Levenstein distance or something like that. You have to do something smarter. This is usually done using the IBM models, which were developed in the 90s when they started getting interested in machine translation again after many years. And they use expectation maximization to figure out which words align with one another. And there are two widely used word alignment packages. Actually, Giza is really widely used. Berkeley Aligner is not that widely used, but I found that it actually gives much more accurate alignments. And it also has the advantage of you can save out a model and then use that model to align other data that you didn't train on, which is not, if it's possible with Giza, it's not immediately obvious how you would do it. And it also saves out the posterior probabilities for those alignments. And that is going to be really important for the graph-based method I'll be discussing. So I'm going to use these alignments to extract scores from narrative retellings, which I'll then use for diagnostic classification. So I said you needed a parallel corpus, and I have 3 parallel corpora I've created just from the retelling data that I have, just people retelling the story. So the first one is small, the second one is a little bit bigger, and then the third one is huge. So the first one is the source to retelling corpus. All I have on this side is the source narrative, and all I have on that side are the retellings. So this is about 500 or so lines long, because that's how many retellings we have. Corpus 2 is a word identity corpus, so we're just saying the word cook should align to the word cook. And because we're doing monolingual alignment, this is a good assumption to make. If you see a word on one side and you see the word on the other side, there is some high probability that they're going to align to each other. The third corpus, the huge corpus, is a retelling to retelling corpus. So every pair of retellings. So this is 500 squared, 250,000 lines. So what I do is I use the Berkeley Aligner to build 2 models. The small model is built just on corpus 1 and corpus 2, just the retelling to source and the word identities. The large model is built on corpus, all 3 corpora. The difference it takes like 2 or 3 minutes to build the first one. It takes like 12 to 24 hours to build the second one. Very, very big difference in time required to build these kinds of models. So I'm going to test both models on the 2 retellings for each of the experimental subjects. So we can see how well they align to one another. And then I'm going to use both models, because you can save out the models with the Berkeley Aligner, to align every retelling to every other retelling, because I'm going to be using that in my graph-based model. So these are the, I'm just looking at time. OK, so these are the results of the alignment, the precision recall and alignment error rate. Alignment error rate is like word error rate. It's sort of a measure of the precision and recall of how many alignment pairs were found in the proposed alignment that existed in the gold manual alignment. And you can see that the AER, you get a very large reduction in AER as you move from the small model to the big model, almost 4 points, which is very, very large improvement for word alignment. But those are still pretty high. State of the art on the Europarl corpus with the Berkeley Aligner is like 4, and we're at 20. So we can do a lot better. So the idea we had was to use a graph-based method that uses random walks on graphs. So you probably all know about PageRank, Google's way of ranking web pages. And it has to do with you build this graph, and the nodes are web pages, and the edges are the hyperlinks between those web pages. And if you were to just walk around on the graph you created like that, the nodes that you end up on would be the more prestigious nodes, the more important nodes. LexRank is a way of ranking sentences for automatic summarization. So for word alignment, the nodes are words in the retellings, and the source and the edges are the normalized posterior weighted alignments proposed by the Berkeley aligner. So we know the alignments and what their posterior probabilities were. So imagine if you had these 4 sentences. The source is on the bottom. These are sentences from our subjects, and you can see that the bold-faced words should all be aligning to touched, okay? But suppose they didn't. Suppose that when you did your alignment of just the source retelling, you only got moved aligning to touch and sorry aligning to touch. So then you align every retelling to every other retelling, and you uncover the relationship that moved aligns with sympathetic and sorry aligns with sympathetic. Now you want to be able to get from sympathetic to touched, and you couldn't do that in your original alignment. Once you build this graph and start walking around on it, you can start at sympathetic and be like, okay, I'm going to go to moved, and then from there you can go to touched. Okay? So the idea is that it creates a connection between words that maybe were unaligned in your original alignment that you can now uncover by virtue of the relationships that word has with other words in other retellings. So we build a graph using the alignments and posteriors generated by the Berkeley aligner. And this is the way the graph works. The walk works. You start at a node, which is a retelling word. With some probability, you move to a word in another retelling. And with some other probability, you walk to a source word and you break. And you do this 1,000 times for every retelling word. And the destination source word that you end up at the most often is your new alignment. So you have a distribution after the end of 1,000 walks of which retelling word, which source word you ended up on. You pick the most frequent one. That's your new alignment. And you can tune the value of this lambda on those 26 ineligible participants. They can serve as a dev set for this. And so I do this for the alignments from both the small model and the large model. And we can see here that if you take the small model and then apply the graph-based method to the alignments proposed by it, you actually get over a 4-point reduction. So it's a larger reduction than you get just by moving to the large model. And keep in mind that the large model takes 12 to 24 hours. This graph-based model takes 3 minutes tops. It's very fast. So you're getting the same benefit with, requiring very, very few computational resources. We also see that the graph-based models both outperform both of their correspondingly sized models as well. So this bodes very well for using graph-based models. So now I want to extract scores from those alignments. And I'll explain how I do it. This is the narrative. The elements are labeled with letters of the alphabet, the 25 elements. And this is a word alignment that the Berkeley aligner proposed. So what we do is we look at the word from the retelling. We got rid of the function words because who cares about them? And we look at a word in retelling, and it aligns to a source word. And we see where does that source word appear in the original narrative. It appears in element A. So this person got element A. Taylor aligns to Thompson. Where does Thompson appear? In element B. Worked, employed, element E, and so on. So that's how we get the scores. So we know for every element, did they get it or not? So I evaluated the scores that you can extract from this. And actually, under all the models, the F measure is very, very high. In fact, I'm giving you the Cohen's kappa. That's a measure of inter-annotator agreement. This is actually within the range of human inter-annotator agreement on this task. So this is a computer performing as well as a person on the task of scoring this test. And in addition, we see that the models with lower alignment error rate produce the higher scoring measures, which we're glad to know. So now we want to use these scores for diagnostic classification. So what we do is we extract scores from each subject's true retellings. Then we use a support vector machine to classify the subjects. We have 2 feature sets. One feature set is just the summary scores. So for each retelling, 0 to 25, how many elements did they get? This is the score that's reported as part of the Wechsler memory scale. The second feature set is the 50 element scores. So for each retelling, there are 25 elements. So we create a vector of 50 scores, each one being 0 or 1, depending on whether or not they got that element correct. And then we're going to evaluate this in terms of area under the receiver operating characteristic curve using leave pair out validation. And so with AUC 0.5 is chance, and 1 is perfect. So anything greater than 0.5 is good, and the closer it is to 1, the better it is. So we can see here that the summary score feature, now the summary score is what's reported normally, it does pretty well. It gets close to, it's about 0.75 for most of them, but actually the element score features are much, much better. And they're getting very high classification accuracy. And another thing to note is that the clinical dementia rating has a reliability at about that level. So you could sort of say that this technique is working as well as humans are at actually distinguishing mild cognitive impairment. And again, we see the large models and the graph-based models are stronger than the ones that are small and not graph-based. So, can I finish?
Oh, yeah.
Okay. It says stop. I was like, all right, well, you're on your own for the summary, people. So the methods outlined here show potential as a screening tool for neurological disorders because it's not just this test that's widely used. There's another test called the NEPSI narrative memory that's used with kids. There are picture description tasks, things like that. So it would be easy to adapt this to other scenarios. And the other thing that was good was that these graph-based methods yielded large alignment error rate improvements without requiring the extensive computational resources that scaling up to a really large model would. So other improvements in the graph-based model, right now it's just one-to-one alignment because I just picked the single highest, most frequent destination node over the distribution. But there are plenty of one-to-many alignments in our data, so that would be something I'd like to look into. I'd also like to look into using undirected links, like having or allowing links out of the source word. I feel like you could be exploring the graph a little bit more than I am. I'd like to apply the technique to other tasks, as I've said, the NEPSI narrative memory task and the cookie theft picture description. This is where you look at a picture of a kid stealing cookies from the cookie jar and have to describe it. I'm working right now on incorporating speech recognition into the pipeline, and with Miter, who's going to be talking about something similar in her poster. And I also want to try to apply the graph-based method to multilingual word alignment. There's a, Europarl is huge. It has lots and lots of languages. It seems like something like this might be able to be used to improve word alignment in some way. So that's all.
Questions?
Hi. Hello.
Hi, sorry.
So what is the accuracy of the alignments if you just map same word to same word?
It's like 40, maybe 30 or 40. So it should, the thing is, like, it should be good because the probability that a word aligns to that identical word is quite high. It's like 60%. But the problem is that there are multiple instances of words. So you have to decide which word you're going to align it to. And I think that's where the inaccuracy comes from.
You talked about kids. Were you talking about specifically about the Wechsler test for kids or another test for kids? And what is the neurological impairment? Because I'm assuming it's not dementia at that point.
Very, very early onset dementia. It's a really terrible problem. So the test specifically I was talking about was the NEPSI narrative memory test. So the NEPSI is like a huge battery of things that test not just memory, but language skills and executive function and all of those different things. And actually, I've already applied these methods to that, and the results, they're not quite as compelling, but we don't have as large a data set. But they're pretty good. But also, if you're familiar with autism at all, there's an instrument called the Autism Diagnostic Observation Schedule that's used to, it's like a series of semi-structured activities. One of them is called a wordless picture book. And the kid and the examiner together narrate a picture book. And this is a technique that could probably be applied to something like that as well. And the neurological impairments we're interested in are autism and language impairment. And actually, the NEPSI narrative memory is very tied to language impairment performance on that.
Hi. One more question. So were you doing the alignment on the entire, like so it wasn't like sentence-based and then match?
So it wasn't sentence-based. It was the full retelling to the full source narrative, which is weird. Like, that's not what you would do in machine translation. In machine translation, you would have it have sentences aligned. But because we don't know in advance which parts of the story the adults are going to remember, you can't do it. You'd have to do a sentence alignment first, and the different story elements might appear in one sentence that appeared in two different sentences in the source. So we just put it all together.
Well, I just mean it because from the point of view of a source of error, like the IBM models are like kind of designed to work on sentences, and kind of imagining that you're doing an alignment on much longer dependencies.
Yes,
like,
so that is almost certainly why, I mean, one of the many reasons why the alignment error rates are much higher than they would be for machine translation.
Thank you very much.
Hello. Hello, everyone. My name is Congle, and this work is done together with Raphael, Hoffmann, and Dan Weld. Dan is my advisor. I'm very glad to come here to talk with you about this work. So, as you may know, relation extraction is a very important task in natural language processing and artificial intelligence. Hope this simple example can help you understand the goal of relation extraction. Suppose we have some raw sentences, like our captain, Janali Jenkins, is a phenomenal athlete, said the Gator's head coach, Urban Meyer. So after a human being read this sentence, he can get some interesting facts, like the Janali Jenkins plays in a football team like Gator, and Urban Meyer coaches the football team Gator. So the question is, can machines do the same thing as human beings, can get these facts and input it into the machines? So formally, relation extraction is a problem that we have an ontology with set of relations with type signatures. For example, an athlete is playing for a team. We have type signatures, athlete and team. We have a relation, plays for team. So our goal is we are interested in the facts of this relation. So we want an extractor the input of this extractor is some raw sentences. The output of the extractor is some tuples, satisfying the relations you are interested in. So suppose the relation you extracted from the raw sentence, for example, like Janali Jenkins and Urban Meyer in this case, is not existing in your knowledge base. You can just add this instance back to your knowledge base, add this instance back to your ontology, and your ontology is becoming larger, better, and more useful. So that's the goal of the relation extraction, and that's the first step to build a better knowledge base to use for other tasks. Okay. At the first glance, you may think that supervised learning is the best way to do this task. So in order to build a classifier for the extractor, what you need is a lot of training sentences. For each training sentences, you need to figure out the entities in these sentences and their relationships. For example, like Ray Allen and Doc Rivers, they satisfy the relationship couched by. You label it as a positive example. And YouTube and Google, you know that Google acquired YouTube actually, but this sentence, like YouTube API in Google code, say nothing about acquired relationship. So you have to label this as a negative example. Okay, supervised learning is good, but what's the problem? The problem is it cannot scale easily. So let's see an example like the ACE 2005 dataset. It contains only 1,500 articles. So the reason that supervised learning is hard is not the problem is that it is not only hard, but it's almost impossible, because the positive data is very skewed. So most sentences actually do not contain any interesting relationships in your ontology, in your small set of relations. So here is a data set. So the ratio of positive sentences actually is less than 2%. So for the top 50 relations in Freebase, which means that if you ask a human labeler to label your sentences, they will meet one positive sentence after 50 negative ones. So I don't think many people have that patience to label enough data for this task. So researchers want to avoid labeling to avoid this kind of labeling sentences stuff, so they propose weak supervision to leverage the instances. The idea is that, okay, it's hard to get labeled sentences, but it's easier to get labeled relation instances. For example, you know that the Gator and Urban Meyer, they've satisfied the relation team coach. You know Google and YouTube satisfy the relation acquired. And it's also very easy to get a list of unlabeled sentences from whatever you can imagine. The clever part of the weak supervision is that you heuristically generate the training examples by matching the instances into the unlabeled sentences, and return all sentences that contain this pair of entities as the training example for your classifier, for your extractors. Of course, it brings in some noises to your extractor, but since the number of labeled sentences is so huge that you can do a lot of machine learning stuff on this kind of interesting data. Okay, life is so good until we ask a question. So what if the training instances here is also small? Because the previous work doing the weak supervision, they try to avoid this problem by only looking at the relation that's already existing in the database, which means that it can get large amount of training instances for free almost. So, but what if you want to define a relation by yourself for some biotask, for some whatever you want, for some question answering? The relation may be very specific. You only have some examples for that. You don't know which database to look at. You don't know where to look at. So we want to solve this problem. So our motivation is that there are some very large background ontology on web. You can leverage these background ontology. They contain like millions of entities and thousands of relations. So what if we can build a connection between our target ontology, our target relations to this background ontology? And there are very likely that among these millions of entities, a lot of entity pairs satisfy my target relations. If I can dig them out, use them as the training instances, I can significantly increase the number of training instances for my task, and I can do weak supervision very well. So that's the idea we called ontological smoothing. So the goal is that I have a relation. I want new training instances. I generated the training instances from the background ontology. The method is that we do an ontology mapping from my target relation to the background knowledge base, to the background ontology. Okay, here is the overview of our system. We call it Velvet. The first step is to build a mapping from the background ontology to the target ontology. The second step is to generate new training instances and the training sentences from the mapping and from the unlabeled sentences. And the third step is to train a relation extractor with this new data. Okay, so what's the challenge to do this job? There are two major challenges for our ontological smoothing idea. The first challenge is that there might not be some explicit mappings. You may ask a question, can I use a very naive way to just pick an automatic relation in the background knowledge and return all its instances as what you need? The problem is that usually good mappings is not explicit in your background knowledge. You need some database operator like join, like union, like selections to get what you want. Here is a simple example. For example, in your target relation, you have a relation coached by. It has an example, Kobe Bryant and Mike Brown. So in your background knowledge, there is no direct connection between Kobe Bryant and Mike Brown. What you know is that Kobe Bryant plays for the team LA Lakers, and the coach of this team is Mike Brown. So for human beings, we can easily see that if I join the praise for team and team coach, I can get a lot of tuples. If I take the first argument and the third argument of these tuples, I get a lot of good training instances for the relation coached by. That's what I want. But how can machine do that? So another, besides join union, is also important because the same relation can be split into different domains in your background knowledge, and they may even have different names. You can very hard to get their relationship at the first glance. For example, like the head coach. The team coach is named as a head coach in basketball domain and a manager in baseball domain. What we want is to put them together in our system. So the output of our system is a view, a database view with the operator of join union selection, and build mappings from the target relation to a view over the background knowledge base. The second challenge is that we do need to do the entity type and relation mapping as a whole, jointly do the mapping. The reason is that the entity is very ambiguous in the background knowledge. For example, you can see that there are many Mike Brown in your background knowledge. One is basketball coach, one is football player, another is a politician. So without context, how could you know which one is the guy you are talking about in your target relation? But under the condition that the coach by relation is mapped from praise for team, join team coach, you have big confidence that the basketball coach, Mike Brown, is the guy you are looking for. Okay, so we can handle these difficulties, these challenges in our system by by breakdown into two steps. The first step is to generate mapping candidates, and the second step is to choose these mapping candidates by the joint inference. So we first put the background knowledge into a graph with each node is an entity in the background knowledge, and each edge is a relation in the knowledge. So we look for the instance pairs in our target relation. We return the paths between them as the relation mapping candidates, and we return the type of these nodes as the type mapping candidates. Such kind of method is sometimes has some problem. It's noisy. You can see that the Kobe is born in USA and Mike's nationality is also USA. This is a parse between the two arguments, and you will return this noisy parse as a candidate. So we need to specify the likelihood to these mapping candidates in order to get the correct ones. So what we do is to use the Markov logical network model, which is good to do the joint inference with the evidence writing in first-order logic. The probability of the event in Markov logic is written by the number of satisfied rules times their weights. And in our work, we have three kinds of predicates, one for entity mappings, one for relation mappings, and another for the type mappings. We write these predicates together in the first-order logic rules. Actually, they are features for our observations, and we conduct MAP inferences to get the predicates, to get the truth value for the predicates, which means that the predicate is true, which means the mapping is good. Okay, to do the MAP inference, we simply cast the problem into integer linear programming, and then do LP relaxation and randomize the roundings to get the result, which is quite standard method in the textbook, so you can check it. Okay, so here we are. Where we are is that we have the ontological mapping. We have a lot of new training instances and training examples. What we need is a relation extractor, a weak supervised method to do the relation extraction. We use multi-R in this project. It is developed by Raphael, Hoffmann in our group. So it might be, to my best knowledge, it might be the only out-of-shelf relation extractor you can find now, and it scales very well to like millions examples data set. So it's a useful tool. Okay, so here's our experiment. We compare our system Velvet against three baselines by taking the joint inference away, by taking the complex mapping away, by taking the smooth instance away from our system. We do the experiment on two target ontology, NL and IC. There are 43 relations. IC, there are 9 relations. We use the freebase, which contains like 100 million facts as our background ontology. So we do the experiment on unlabeled data sets, unlabeled sentences of New York Times, which contains also millions articles and like 50 million sentences. Here is our performance. So you can see that without smoothing, it's not surprising that without smoothing performs very bad because the system is trained only by like dozens training examples. By putting complex mapping and ontological smoothing into the system, the performance is improved significantly, and Velvet is the best of all. So the last slide shows the figures averaged by instances. We can also average by relations. This result, the results in the last slide may be a little too optimistic because big relations is easier to do than the small relations. This is averaged by relations. We can also see that Velvet is much better than the baselines. We also compare our system, our method, to the current state-of-art supervised extractions on the Cornell 04 dataset. We use two state-of-art supervised approaches as a comparison, and we do the experiment. Our system use very few training instances, only 10 ground instances per relation. There's no sentence annotation. It's surprisingly that we can achieve comparable result to the state-of-art supervised method. It's because we use large number of unlabeled data sets. So they are trained by like 1,000 data sets, but 1,000 example sentences. We are using like millions unlabeled sentences. That's why we can get comparable performance. Okay, we also evaluate the performance of ontology mapping itself. We manually label some mapping results of NL, and we achieve like 88 accuracy on relation extraction and 93 accuracy on entity mapping. So the result is like 5% better than the baseline, which is a free-based internal search API to get entity mapping, which is about 88. Okay, so our system, so we noticed that the previous weak supervision doesn't scale very well because if you have very few training instances, so our solution is to use background knowledge, background ontology to generate ontology mapping to bring you a large number of new instances. It can enhance relation extraction performance very well. Well, here are some future work. For example, we are planning to bring multiple ontologies, do the mapping to multiple ontologies. We are also interested in so not only binary relation, but also n-array relations. For weak supervision, there are also a lot of space to improve, like the data is very skewed, and the future is extremely high dimension. So it sometimes makes the performance quite hard to improve. So there are some future works to improve. Here it is.
Thank you very much. We have some time for questions.
So I wanted to ask you a question about n-array relations, and then you put it as future work.
Yeah.
And but I was also thinking, do you really need n-array relations? Because maybe you can do everything with binary relations. So where do you see the benefit of dealing with n-array relations?
So I think the n-array relation is that you sometimes. So you can break the things. You can break the n-array relation into several binary relations, and there is a major entity. That's the simple way to do the n-array relation. But I'm not sure if it's good for all situations. Maybe there are some cases it will not work very well. For example, if if many arguments are like the date or numbers, I don't think it will work because I'm not sure if it will work because these arguments are related to each other. So if you treat each of them as a binary, there may not be many linguistic evidence to get them. I don't know.
Yeah,
maybe it's the case.
I might have missed this, but did you evaluate the precision of the relations you're generating from the smoothing, or are they sort of 100% correct? So you have some seed relations, and then you get more from, or some seed examples, and then you get more from Freebase. Are those like sort of 100% correct?
Oh, I know what you mean. So what's the precision of the examples? Oh, I didn't label that. Yeah, this is a good question. So we only label that by using them and to train an extractor what's the performance, but I didn't sample the instances and to see what's its performance. Yeah, it's a good question.
Makes sense.
We didn't do that.
All right, then. Thank you very much, and we'll move on to our last oral presentation by Max Whitney.
Okay, so I'm Max, and this is work with my supervisor, Anoop Sarkar. And the topic of our paper is bootstrapping, which is the case of semi-supervised learning where there's a single domain and there's a small amount of labeled data or seed rules. Okay. Oh.
Is your mic on? Can you just check?
It should be.
Oh, it is? Okay.
Okay. Okay, so bootstrapping. And in particular, we're looking at the Urowski algorithm, which is a simple self-training algorithm with decision lists. So we start with some seed decision list, we label the data, and we train a new decision list and repeat. And a decision list looks like this. The running example here is word sense disambiguation on the word sentence. So one sense is a piece of text and one sense is a punishment. So here we have two seed rules. A rule is a score and a feature and a label, a sense. And the decision list works just by choosing the highest ranked rule which has a feature matching the example. So here when we apply the seed rules to data, the first two examples in the data can be labeled because they have a feature that matches the rule, and the third one can't be because it has no feature that matches. So that's the first two steps. In the third step, we train a new decision list, and the scores are coming from statistics over the currently labeled data. So it's basically co-occurrence with the previous rules. And you can see that now we have more rules. We can label more of the data, but we have a threshold. We only take good enough rules based on the score. So we're never guaranteed to be able to label all the data, just whatever we have features for. And we repeat. At the end of all of this, we'll drop the threshold, make a decision list with no threshold, and then we can label all the data. So we do that for testing. This is sort of similar to EM, or hard EM at least, but the difference is that we're training this decision list model, which contains type level information. Whereas EM is, you have expected counts over the actual instances, the token level. So to examine the behavior of this in more detail, we're going to continue with the same example. Now the current decision list is on that side, and we're just showing the two senses with the colors. And the currently labeled training data is going to be down there, also labeled by color. So in this graph, the left bar is going to represent the decision list, and the right bar is going to represent the currently labeled training data. And up here, we're going to show accuracy, the current test accuracy with the decision list. So as we proceed, the decision list, that's the left bar, is growing very rapidly. And we've now labeled, I believe that's all of the training data. And you can see that both are kind of skewed towards the blue label, whichever sense that is. And now that we've labeled all the data, the accuracy kind of plateaus. And we converge there at about 60% accuracy. So the next variation is Urowski cautious, which is from Collins and Singer. I didn't say that we're using Collins and Singer for our particular specification of Urowski and Urowski cautious. And here, for cautious, when we make a decision list, we take the top 5 rules by score, and then at each iteration, we take 5 more. So the decision list is now going to grow linearly. And you can see that, whereas in the previous example, the axis went up to 1,800, now it's only up to 400 because we're controlling the decision list. So as we run it, the decision list, that's the left bar, is growing linearly, and it's balanced between the two features now. And the coverage and the accuracy are going to grow more gradually, and we converge at a higher accuracy. So now this is our non-cautious, and this is our cautious. Both will change when we do a retraining step, and we drop threshold and we drop cautiousness and train big decision lists. But usually we see this behavior, that cautious avoids getting stuck at low accuracy. So the reason we're interested in Urowski is that it seems to do pretty well. The first 4 here are our own re-implementation of Collins and Singer. And the last is a version from Abney, which we'll talk about a little bit later. And you can see here that the co-training algorithm and Urowski cautious are the best of that set. And Collins and Singer also have an algorithm called co-boosting, which does comparably in their results. We haven't tested it. And you can also see that the cautious algorithms, Urowski cautious and co-training, which does something similar, are the only ones that get up to about 90%. So cautiousness is important. And the reason we're interested in Urowski over the other algorithms is that co-training and also co-boosting require 2 views, and the views are supposed to be independent. So it's nice to be able to drop that limitation and just use self-training. So that was the upside. The downside is we don't have very good theoretical analysis for Urowski. There's no proven bounds. Abney, in this paper, addressed that, but only for certain variants. And those variants are not cautious. And he doesn't give empirical results. We don't think that they would do as well without cautiousness added. Hafari and Sarkar extend this analysis, and they use a bipartite graph representation, which we'll see in just a minute. And we do have empirical results, but it's not cautious and therefore does not do as well as what we just saw. So here's the analysis. We're going to look at two types of distributions. This is the parameters. So it's a distribution for each feature over the labels, and that's the labeling distribution with a distribution for each example over the possible labels. So the labels being the senses in the example we saw. So the labeling distribution is uniform if an example is currently unlabeled, and otherwise it's a point distribution with mass on the label. And the parameters are just the decision list scores, except that we've normalized them to be a distribution. So a decision list will make this choice just taking the maximum scoring feature from an example. And Abney introduces this alternate form where we take a sum instead. It's not quite a decision list, but it is easier to analyze. Okay, so switching topics slightly, Subramania et al. Have an algorithm more recently which they use on a part of, what is the task? I believe it's part of speech tagging, and it's a domain adaptation thing. So it's a slightly different task and a slightly different algorithm, so we're not concerned with the details of their algorithm, but a couple of interesting properties. And this is self-training with a CRF. So you can see it's had these same two steps where we label data and train, but they've added these extra steps, one to get type level information and one to do graph propagation on top of that. So the two things we're interested in here are first the overall structure, the adding of these steps, and second the particular graph propagation they use. So our own contributions for this paper, number one, we have an a Urowski variant with a per iteration objective, which we'll see in a minute. And this algorithm is cautious, and we can show that it performs well. So unlike the previous well-analyzed Urowski algorithms, we show that it can do as well as Urowski cautious. Second, we've unified all these different approaches, the different algorithms. And third, more evidence that cautiousness is actually important. So going back to the graph propagation, this is an objective from Hoffmann and Sarkar for one of Abney's Urowski algorithms. It's an upper bound on the algorithm. And this is the objective for the graph propagation part of Subramania. It's not the objective for the whole algorithm we just saw, just for the graph propagation step. And you can see in the first equation, this is the labeling distribution, that's the parameters again. So if we compare these, the first term of each is going to be the distance. If we plug those distributions into this, it's going to be the distance between the parameters, the decision list scores, and the current labeling. And the second term is a slack or regularizer. So they're quite similar. So if we do plug those distributions into this, then we can directly optimize that model, the bipartite graph model. Alternatively, we can not use that motivation from Hoffmann and Sarkar, but we can just do graph propagation over the thetas, the parameters, where we take co-occurrence in an example to be adjacency. So it's not as well motivated from that work, but it sort of corresponds to what Subramania et al. Do. So here's our own algorithm. It's like Urowski, but it has this extra step. So first we train a decision list in exactly the way we saw with cautiousness. And second, we do propagation over that. So we just take the parameters and we make one of those two graphs and we propagate that. And Subramania et al. Give iterative updates to do that propagation. So we can either do it on the bipartite or the unipartite graphs that we saw, or a couple more which are in the paper. If we use the bipartite one, we only take the parameters at the end, the decision list part of the model. And so because we're doing this step, we know that at each iteration, we're optimizing the objective that we saw. And we can do cautiousness simply by copying the decisions of this decision list, the original decision list. So this one determines which examples we'll label, and this one determines what the labels actually are. So to look at the behavior of this algorithm, we'll do the same visualization. And so again, the left bar is going to be the decision list, and the right is the labeled data. So you can see that, like in cautiousness, we're forcing the decision list to grow linearly and balanced between the two labels. And now we're labeling, because of the propagation, we can label more examples sooner. And the accuracy is increasing sooner. And comparing to what we just saw for Urowski cautious, we're actually doing a bit better in this case. Again, they'll both change when we do a retraining step and make a bigger decision list. But the behavior is a bit different. We increase coverage and accuracy quicker. We can also look at what happens to the objective. This is the objective from Superman, just the graph propagation part. And here we've disabled cautiousness because cautiousness, by changing the input to the graph, it's changing the objective a lot. So without cautiousness, on the bipartite graph, this is the objective globally, and it's decreasing, and it kind of levels off as the accuracy and the coverage level off. So we have two sets of experiments. The first is following the running example. So this is Eisner and Karakos's word sense disambiguation data from the Canadian Hansards. There's 3 words, each of which is ambiguous in English but not in French. And each has 2 senses and 2 seed rules. The features are the words adjacent to the word we're looking at and some nearby context words. And we use the lemmatized and raw forms of each. So this group of algorithms is the ones we've seen. This is Hafari and Sarkar's algorithm based on the bipartite graph, and that's a different kind of graph propagation. And you can see it doesn't do as well. And this is our algorithms. So in this case, the cautious form of our algorithms, this is the bipartite one, and this is the unipartite one. And you can see the unipartite one is doing pretty close to DL co-train and cautious. It's actually beating cautious. And the bipartite one's doing pretty well, too. The data here is a little bit strange. The data sizes are small. The second task is this named entity classification from Collins and Singer. And in this case, we have 3 labels: person, location, and organization, 7 seed rules with some for each label. And the features are spelling features, which are from the phrase we're classifying, and context features, which are extracted from a parse tree of the sentence. So particular words nearby in the tree and the relative position in the tree. And again, the algorithms we've seen, this one, and our algorithms. And again, the theta only, the unipartite one, is coming out quite well, and the bipartite one's not bad either. In this case, our algorithm is the top, but we're not really trying to show that our algorithm is beating Urowski cautious or DL co-train here. We're just trying to show that it is coming out equivalent in accuracy. But as we said, it doesn't have the disadvantage of requiring 2 views. Well, I didn't say we're reporting non-seeded accuracy here. So that means we take accuracy only over the examples that the seed rules do not label. So the idea is to measure improvement over the seed rules, not what we were given. And that's it. So we have software online if you want to see. Thank you.
Thank you very much. Sorry about that. Wait for the mic to come on. So we have time for a few questions.
Hi, great talk. I wasn't able to figure out if the algorithms are able to, once you label an example, in later that example is to escape from the labeling and go back to the unlabeled. Data set.
Yes. Yeah. The steps are.
I mean, I saw that the labels are always increasing, but.
Yes, but we relabel the entire data at every iteration. So an example can become unlabeled. It doesn't happen very often, but it is possible.
Can you elaborate on the problem of requiring the two views? So how bad it is, and in practice, what?
I don't know how bad it is in practice, but my understanding is that the theoretical requirements for those algorithms are that the two views are statistically independent. And so you only get the theoretical properties if your features have that property, which is quite unlikely. And so the idea is that we can get the same performance with a much simpler algorithm without having to have that property.
Okay. But, I mean, the performance is on a specific data set that doesn't have those properties, I guess.
Well, on the data sets we've seen, it's doing comparably to the co-training algorithms. So we don't know that it's better, but it's doing it comparably, and we don't have to have the requirement on the views.
Also, we had to try many different ways to split the features for the word sentence data, and we picked the best one. But we had to do a search, there was no natural, so nearby and far away is not necessarily a natural split of features. So it's better, the machine learning technology, you should not have to think about it, right? You plug it in and it should work, so why do this extra work if you don't have to? So never do code training and always do your ASCII.
Okay, then that's going to conclude our second oral session.